Hello everyone, I'm Hijikata from Saitama University, Japan. Congratulations! The third Asia Pacific Conference on Silicon Carbide and related materials is now coming back from a worldwide COVID-19 pandemic. I sincerely thank to all people who may concern this great conference and respect their enormous efforts. Thank you, and see you later. Hello again. I moved to my office. Now let's start my presentation. So first of all, I am very honored to be here as an invited speaker. I would like to thank all of the program committees for this great opportunity. Today, I'd like to talk about single photon sources in silicon carbide, so not power devices, unlikely to other presentations. The title of my talk is Characteristics of the single photon sources formed at the MOS interface. First of all, I would like to thank to all whom this study has concerned. Master course students and OBs of my laboratory, Takeshi Oshima and his group members of National Institute of Quantum Science and Technology, and Yuichiro Matsushita of Tokyo Institute of Technology. This is the outline of my talk, starting with the potentiality of recent quantum technologies. Next, I'll show some single defects in silicon carbide and their merit for quantum technologies. After introducing surface single photon sources, finally, I would like to conclude my talk. So let's start. Today, just opening the door to the quantum technology's age. Because of the fragile of quantum, high sensitivity sensor can be expected. In addition, quantum encrypted communication is also expected because the communication is never tapped based on the uncertainty principle in quantum mechanics. And smallness of quantum enables us a high resolution measurement. Because of randomness of quantum bit, namely quantum superposition, used for quantum computer can be realized. Now I would like to switch to quantum bits, so-called qubits, which is often used for quantum technologies. So let's consider which qubit is suited for silicon carbide. Electron spin is realized especially from superconductors, and elementary charge is from semiconductors. However, I believe most suitable qubit source is photon. If we utilize the photon, a superposition between p polarization and s polarization can be utilized as a qubit. There are features of photon qubit. Because of light independency, it's free from electromagnetic noise and crosstalk free, even in precise circuit lighting. It propagates in free space straightly, so it is unnecessary to contact to a terminal. And there are some room temperature bright single photon sources. On the other hand, photon is difficult to confine, so it's difficult to amplify and conserve. However, as will be mentioned later, optical resonator might solve these problems. This slide shows quantum state and polarization state of photon. Bloch sphere indicates quantum state. The north pole corresponds to 0 state, and the south pole corresponds to 1 state. Also, the XY coordinate indicates the quantum phase difference between 0 state and 1 state. On the other hand, Poincare sphere indicates polarization state. Stokes parameter S1 corresponds to the horizontal or perpendicular direction in linear polarization. S corresponds to plus minus 14.5 degree direction in linear polarization. S3, namely latitude of the sphere, means the degree of right circular polarization and left circular polarization. It should be noted here, the Bloch sphere and Poincare sphere are completely coincident with each other. Next, I'll talk about the single defects in silicon carbide and their merits for quantum technologies. Because silicon carbide bond is strong, which makes crystalline relaxation difficult. A lot of single photon sources were found. Hereafter, I call single photon sources as SPS. In case silicon atom is loosened, silicon vacancy is formed. Its spin quantum number is 3/2. The radiation is ranged at the near infrared region. In case C is loosened as well, its divacancy, whose spin number is 1, radiation is at infrared region. Carbon antacid vacancy pair is formed from silicon vacancy after carbon is moved to silicon site. They have very strong monochromatic visible radiation, but no spin in the defect. Also, NV center in diamond is very famous in the quantum research world. SiC also has the NV center. However, while the diamond NV center is visible radiation, SiC NV center is predicted to be infrared radiation. Furthermore, silicon carbide has a high brightness, room temperature electrically controllable SPS, which is so-called surface SPS. Today, I'll focus on this type of SPS. Next, I will introduce the SPS formed on the silicon carbide crystal surface, so-called surface SPS. Before the explanation of surface SPS, I will introduce my confocal fluorescence microscope system. This is a schematic illustration of our confocal fluorescence microscopes, so-called CFM. CFM is one of the super resolution microscope, which has a resolution over optical diffraction limit. Because the incident light to sample and detector have a confocal systems to avoid stray light, resolution can be enhanced dramatically. All the photoluminescence PL maps coming out later were basically obtained from this CFM system. This is a photograph of our CFM. Next, I will talk about what is the surface SPS. These figures show PL maps before and after oxidation, and oxide removal, and oxidation again. Before oxidation, we don't see any SPS. But after oxidation, a lot of SPS appeared, like this. When removing oxide layer, single photon intensity remarkably reduced. And SPS appeared again after reoxidation. Therefore, oxide layer plays an important role to enhance PL intensity. In addition, polarization properties indicated the linear polarity, and their polar angle agreed with that of substrate crystalline orientations. Therefore, the surface SPS originates from complex defects existing inside crystal. Next, I will introduce our achievements on the surface SPS. We attempted electronic control of the surface SPS using this surface SPS embedded PN diode. As a result, we succeeded in control of a single photon emission by electric field or electrical current. Next, I will talk about the single photon control by stacking fault. SiC is a very unique material. Stacking fault, another word, plane defect, is equivalent to quantum well. So we investigated whether there is a difference between SPS near stacking fault and far from stacking fault. As a result, SPS near stacking fault has much higher single photon emission rate. Therefore, light amplification can be expected using multi-quantum well formed by stacking fault array. Next, I'll switch to studies on structure identification of the surface SPS. Although the surface SPS exhibits good properties such as high bright emission and room temperature electroluminescence, there are some problems to solve before practical use of them. One is their radiation spectra are generally broad, which is influenced from a phonon sideband. Another one is variation in radiation wavelengths of each SPS, which is probably due to the influence from amorphous layer at oxide silicon carbide interface. Anyway, it is very important to elucidate the defect structure of the surface SPS. Firstly, we investigated the presence of oxygen using isotope oxygen. Because 18 oxygen has a heavier mass, fewer phonons should be generated when inducing optical transition. In addition, the zero phonon lines energy of 18 oxygen should have higher energy according to this basic spring mass theory. These figures show histograms from 60 surface SPS for center peak wavelengths and peak widths. As we can see from the left figure, much more sharp peaks were aroused from 18 oxygens. Also, such sharp peaks concentrated on 615 nanometers for 18 oxygens and 614 nanometers for 16 oxygens, which is corresponding to the mass difference. Furthermore, the broad peaks for 16 oxygen were a little wider, which is probably attributed to more intense phonon sideband. This figure is histograms on PL intensity, which shows higher intensity SPS seen from 18 oxygen sample. From these results, we can say that difference in optical properties reflect the difference in mass between 18 oxygen and 16 oxygen. So the surface SPS is a defect that contains oxygen. We also attempted analysis of transition level by performing first principle calculations. We assumed some complex defects, including oxygen, like this. As a result, the candidates for defect structures were successfully limited to these 4 types. We also attempted to elucidate the reason why the wavelength variation occurs, studied by first principle calculation. As you may know, there are a lot of interface traps at the silicon carbide oxide interface. According to Matsushita et al., such interface traps are attributable to the interface amorphous silicon carbide layer. Because such amorphous layer equivalent to stacking fault, and stacking fault induces a conduction band fluctuation. Accordingly, we simulated these oxygen defects in 3 different locations in the vicinity of stacking fault. As a result, radiation gaps were changed with location, as can be seen from the figures. Therefore, we concluded that this wavelength variation is attributed to the location relationship between SPS and stacking fault. To prove the change in MOS interface structure makes change in radiation energy experimentally, we attempted to confirm by investigating the post-oxidation annealing for the surface SPS. These figures show the radiation spectra after annealing at various temperatures for one surface SPS. As shown in figure, there are three cases. One is intensity was lowered as increasing annealing temperature, and the other one is changing the defect structure itself. On the other hand, there is a case that annealing makes the shift in radiation wavelengths shown in the middle figure. Therefore, we conclude that the variation in radiation energy for the surface SPS is due to the changing MOS interface structure. Finally, I would like to conclude my talk. These are my conclusions. To elucidate the defect structure of surface SPS, we compared optical properties of the surface SPS formed by isotope oxygen, 80 oxygen, with that of natural oxygen. Also, we performed the first principle calculation to derive defect levels and to clarify the cause for ZPL variation. According to isotope oxygen measurements, we found that the defects originating in surface SPS contain oxygen. From the calculations, several candidates for defect structure were proposed. Furthermore, the cause for energy variation was clarified, which is probably attributed to the stacking faults at the MOS interface. Okay, my talk has been finished. Thank you for your kind attention. So I finished my talk. Thank you again.